Morning. Hello. Today we're going to continue to talk about hardness versus randomness. I'll remind you where we kind of were last time, and then I'll read what's on the board. Right. So last time we were in the middle of like a grand plan to show that BPP equals P, subject to some assumption. And Nisan-Wigderson proved this in 1994, subject to the following assumption, that there's a super hard function for circuits in the complexity class E. Things that can be computed in time 2 to the order n. And super hard means that given any circuit of size, like maybe 2 to the 0.0001 times n, it can hardly do a good job at all at computing the language on inputs of length n, meaning that its correctness probability, if you give it a random string of length n, is barely more than a half, and barely more being like a half plus 2 to the minus 0.0001 n. Okay, so that's a believable but very strong assumption, and we're later going to see in this lecture and the next lecture that that assumption is true subject to a much weaker looking assumption, simply that there exists a language in E that cannot be computed exactly by circuits of size 2 to the delta n. But for now, we're going to work with the harder assumption, or the stronger assumption, that there's a language in E that cannot be even slightly, computed much more than on half the inputs by a circuit of size 2 to the delta n. And we're going to show that BPP equals P under that assumption. And we're going to do that using pseudo-random generators. So we're going to use this super hard function to construct a pseudo-random generator. I'll remind you what that is later in this lecture. But a pseudo-random generator that stretches order log n length strings to length n strings, such that if you give the generator a random length order log n string, the output length n string is really good at fooling polynomial time algorithms and can be used to de-randomize BPP to P if you just enumerate overall order log n length seeds. Okay, so I'll remind you a bit more of that later, but last time we saw, if you had a super hard function, how you could build a pseudo-random generator that stretched L bits to L plus 1 bits, which was like a good start, but we want to stretch L bits to like almost exponential in L bits, and we're going to do that today. And when we stretched actually L bits to L plus 1 bits, the hardness of the hard function we were using to construct the pseudo-random generator was like way overkill. It was like much more than we needed, but to get this much longer stretching PRG, we're going to need this super hard function. Okay, so in order to, I'll tell you, I actually told you the construction of the pseudo-random generator out of the hard function or hard language last time. I'll remind you of again later. But in order to prove that it's a pseudo-random generator, we're going to need this theorem due to Yao, which was originally created by Yao in the context of cryptography, but it can be used for complexity theory. And this theorem will help us reason about when or when isn't a function a pseudo-random generator. So let's take a look at this theorem statement. It's called the next bit prediction theorem. And it says, OK, on one hand, suppose you have a random string, u1 through un. And remember, it's like a little bit annoying, but we're going to call our bits 0 and 1 rather than plus or minus 1, just a change of notation. So imagine these are fully independent, 50-50 random bits, plus or minus 1 through plus or minus 1. And on the other hand, imagine you also have just any old random bits at all, z1 through zn. These n random bits can have any joint distribution. They're not required to be independent or uniform or anything. They're just n some kind of random bits. And you should imagine these are like the output of a pseudo-random generator. Okay. And suppose, and because we're going to, when you're reasoning about whether or not something is a pseudo-random generator, you kind of always work in the contrapositive. You assume that you have a circuit that can break the generator, that can distinguish between truly random bits and pseudo-random bits. And you use it to you build from it some circuit that is good at computing your supposedly hard function. So we suppose that we have a distinguisher circuit, C, by which this distinguisher just means this. So that C outputs plus or minus 1. You can think of that as like accept or reject. And on one hand, if you give it totally uniform bits and look at the fraction of times it accepts or its expectation, this is the number between minus 1 and 1, versus the expectation of it given these z's, which is maybe the output of a pseudo-random generator, these two numbers are noticeably different. They differ by at least epsilon. So in some sense, C is pretty good, or at least a little bit good, at distinguishing totally random string from pseudo-random string. Then there exists a good predictor circuit C prime. What do I mean by that? So first of all, there exists some I. Maybe it's like n over 2. Maybe it's whatever. It's like some position I. And a good predictor circuit C prime, which takes in I minus 1 bits. This predictor circuit has no bigger size than the original circuit C. And what does it mean it's a good predictor circuit? It means this. So let's stare at this for a second. What's going on here is you're feeding in C prime the first I minus 1 bits from Z. And you're kind of trying to tell how good is C prime at outputting Zi, the next bit. Okay, remember, our way of measuring like how good, with plus or minus 1 notation, how good like, C is at computing something is to like multiply those two things together and take the expectation, right? Because if C prime's output equals Zi, this whole thing counts plus 1, and if they differ, this whole thing counts minus 1. So the expectation of that, if the expectation of that is like a little bit bigger than 0, it means that like the probability of C prime equaling Zi is a little bit bigger than a half, correspondingly bigger than a half. So here, it's like a little bit bigger than 0. We actually lost a factor of n, but that's actually not going to be a big deal because the epsilons we're going to be dealing with are like, exponentially small or sub-exponentially small quantities. So a factor of n is not going to be a big deal. Right, and it's saying this C prime is a pretty decent predictor, a slightly good predictor. Okay, and so it's kind of sort of believable. I mean, it's reflecting the fact that C prime can kind of notice, or C or a small circuit can kind of notice that these bits are not uniformly random. Of course, if these were truly uniformly random, having the first I minus 1 of them wouldn't help you at all in guessing the ith one. But this is saying that you can, for some value of I, be pretty good at predicting the next one. Yep?
Why do you want to have, why does the theorem only give you there exists an I? Why is it that, why didn't you just like always predict the last bit or something like that?
Well, you'll see from the proof that we don't have too much control over it. Basically, what we'll ultimately show is that like you can actually create circuits, I guess, like C1 through Cn, where the ith one is trying to predict the ith bit from the I minus 1 previous bits. And you'll show that like the sum of their like advantage in predicting is at least epsilon. And then we'll just say, OK, therefore there exists one that has advantage at least epsilon over n.
I think it could be just the case that, for example, the last bit could be truly.
Right, that's another thing.
That's why you cannot predict the last one. So.
Right, it could be, for example, that like Z2 through Zn are actually totally uniform, and Z1 is just like always 1, or maybe it's 1 with probability of 51%. So the C here, which is good at distinguishing, it just like totally zooms in on Z1 and just goes with that because Z2 through Zn are actually uniformly random. So in that case, the only one I would work at all, and that I would be 1. Because it would be C prime would take no inputs and be good at guessing Z1. Yep?
I guess the weird thing is that you get less information if you choose I to be lower, but I just.
Yeah, I mean, this again like has like an unnatural dependence on, in some sense, on the ordering of the bits, but like, it's not gonna matter. Yeah, this is maybe not the strongest thing you could say, but it's gonna be good enough for us. Yeah, I mean, there's no particular reason that like you use these bits in this order to predict this one, but anyway. OK, so this will be similar to like the analysis we did when we analyzed the L to L plus 1 stretch generator, in the sense that it's kind of just messing around a little bit. But it does actually introduce one important tool from cryptography called the hybrid method, which is used a lot in theoretical cryptography and will be used for this proof. And a hybrid method is, well, you'll kind of get the gist of it when I write this. So define a string, well, a bunch of strings, h superscript I, to be, you start with all the z random variables, and then for the first I of them, and then put in all the u random variables for the next one. So I actually defined n plus 1 different strings here, which are like combinations or hybrids, if you will, of the two random strings we're talking about. OK, so h superscript 0 is the same as u, and h superscript n is the same as z. Or, capital Z stands for the string of all z's. OK, so then, this is h0, this is hu, and we're going to imagine like the expected value. I mean, just imagine in your head the expected value of c on h I, so I goes from 0 to n, you go from this number to this number as you go along these numbers. And like the two numbers at the endpoints differ by at least epsilon. So there has to be some value of I where the two numbers differ by at least epsilon over n. Okay, so like without writing all the details, by star and like the telescoping, if you will, and the triangle inequality, or just what I said in words, there must exist an I such that the expected value of C, when you give it the, let me get the indices right here, I minus first H minus, when you give it the ith H, is at least epsilon over n. Okay, and this is the essence of the hybrid method. Like if you have, I don't know, two random variables that you can somehow distinguish, and they have maybe n components, you like kind of hybridize between them in like n steps, and you'll get like sort of two like neighboring random variables or very similar random variables that you're good at distinguishing with the loss of factor of n. Good. So where are we here? So just let's write out what this means. I slipped this by you yesterday, but I want to like get rid of the absolute value signs, and I can do that sort of without loss of generality by like replacing C by the negation of C in my head. And if not gates don't count for anything in the size, which let's say they don't, then this doesn't change the size of C. Okay, so therefore, without loss of generality about C going to minus C, what this is saying, just I'll expand it out slightly, is the expectation over Z and U of C of Z1, Zi minus 1, and then a U, Ui, and then Ui plus 1 to Un, minus C of Z1 through Zi minus 1, and then Zi, and then Ui plus 1 through Un. It's bigger than epsilon over n. Okay. So I guess I also used linearity of expectation to put everything inside one big expectation. Good. And now we have the same random variables here. So if the expectation of this giant quantity inside the expectation is bigger than epsilon over n, there exists like fixed outcomes for these random variables such that the expectation is still at least epsilon over n by, I don't know, the principle of averaging. So therefore, there exists like fixed strings Ui plus 1 through Un, fixed bits, such that, well, this thing still holds with those bits fixed. So the expectation here is over Z. And I guess really now the only random Z's that play a role are Z through Zi. And Ui is left. C, let me write it like this. C prime of Z1 through Zi minus 1 Ui minus C prime of Z1 through Zi minus 1 and Zi greater than epsilon over n, where C prime is defined to be C just with like the last bunch of bits hardwired to these fixed values, Ui plus 1 through Un. Okay, and now I claim we're basically done. Like, this is a circuit C prime. Its size is at most that of C, because we get it from C just by fixing some inputs to some values. And now let me also write it kind of like I'll just undo the linearity of expectation. And so basically what's going on here is on one hand, like you imagine giving C prime Z1 through Zi minus 1 plus a uniformly random bit at the end versus giving giving C prime Z1 through Zi minus 1 and Zi at the end. And like it's sort of good at telling the difference. The expectation of C prime's output here is bigger than the expectation here by epsilon over n. And this is basically what we want. And in fact, it's exactly what we had in the L to L plus 1 pseudorandom generator situation, where this basically means that Z prime is good at telling the difference between its last bit being uniform, given the Z's, versus it being Zi, given the previous Z's. Okay, and so skipping a little bit here, but like it's very similar to the L to L plus 1 PRG analysis. If you recall, we spent like 10 minutes like imagining, okay, there's a half chance that UI equals Zi, there's a half chance that it doesn't equal Zi, and like writing out some expressions and subtracting them. And I'll call it an exercise, therefore. We're basically done. So in fact, if you just repeat the same analysis, you get something that looks like this. There exists a fixed constant, fixed bit B0, such that like C double prime, C prime of Z1 through Zi minus 1 and B0 times B0 is the required next bit predictor. Okay, so I'm going to call that the end of the proof. Okay, any questions about that? This is sort of the most basic use of the hybrid method, so it's nice to see it.
Will it be, because I didn't know that stuff. So will it be 2 epsilon over n or not? After we did that 1/2 y is equal to Zi or not?
I believe it's exactly epsilon over n. But if it's not, that's cool. I mean, we're already using factor of n, but I think it's not. I think it's exactly epsilon over n. Okay, good. So let us sort of save this in our minds. In fact, I might have to erase it. So just one more time. If you have a circuit that's good at telling the difference between uniformly random string and some like pseudo-random string, then there's going to be some position I and a related circuit C prime, where C prime is good at predicting the ith pseudo-random bit from the previous I minus 1 bits. Okay, so now let's get back to the story of Nisan-Wigderson's pseudo-random generator for showing BPP equals P. So I'll remind you of some definitions that are going to take a while to write, but bear with me. So a pseudo-random generator with like some fixed choices for some of its parameters. So if seed length L of n is this, it's really a function that takes like any string and outputs a longer string with the property that like if you give it a length L string, it outputs a length n string. So it's a family of functions mapping, oops, I guess I should use plus or minus 1 notation, L-bit strings to n-bit strings. It's uniformly computable in singly exponential time. That's going to be OK if you recall, because, or what's OK if you recall, because this L is going to be like order log n. So this is just polynomial time, which is good. Such that for all n, and like it's actually annoying, it's technically almost all n. But let's not get overly caught up about that. And all circuits C that are n-input circuits of size at most n cubed. That's like a slightly weird parameter setting, but basically we had to go against, for a BPP algorithm by padding without loss of generality at random linear time. We could convert it to a quadratic size circuit. So I mean, it's going to be enough to fool like n cubed size circuits. And I guess in our definition of size, we should make the NOT gates free. OK, finally, let me write the key point of the pseudorandom generator. It's simply that the circuit can't tell the difference between a uniformly random input and the output of the generator. So I can write it like this. The expectation when you choose S, a length L seed, and give C the generator applied to S, versus when you give it a truly random string of length N. These things are about the same. So it's enough for them to be the same up to some fixed small constant that's smaller than a third. OK. So that was the definition of a pseudorandom generator. And we observed that if you have such a thing, then BPP equals P. Now, remember, we're going to be building it out of some kind of supposedly very hard to compute for circuits function. And the idea was to take a string of length order log n, and the output of the generator would be the hard language or the hard function applied to many subsets of the string, where these subsets are kind of big but don't overlap too much. Okay, so that led us to this combinatorial definition of a so-called design. So an L, K, D design is a family of subsets of 1 through L. Let me give them names. K1 through Kn. That's a big K. Of L. Each of size little k. So hopefully it's OK that capital K is of size little k, such that any two of them have intersection size at most d. So Ki intersect Kj is at most d for all I not equal to j. And what we hastily proved last time at the end of class is just a very simple combinatorial lemma that said there exists designs with reasonably nice parameters. And it's just given n and any constant c in poly n time, you can construct a design with L being c log n, and k is a root c log n, and d is 10 log n. Great. OK, so c is going to be some very, very large constant for us, because this is going to be the length of our seed, some big constant times log n. And what it's saying is that you can get lots of subsets, n subsets. Of course, the total number of possible subsets is n to the c, but think of c as a huge constant, like a million, 1,000. You can find n subsets of here, each of size also about constant times log n, albeit a smaller constant, such that all their intersection sizes are very small, at most 10 log n. OK, and that's exactly what we're going to use to construct the pseudorandom generator. So now, finally, I can restate Nisan-Wigderson's theorem about how to get a pseudorandom generator that makes BPP equal P. OK, so suppose we have this language A that's in computable and exponential time, such that for all, well, almost all, let's say M. Do I want M? Yeah, let's say M. In all circuits C of size at most 2 to the delta M, the correlation of the circuit with AM, this A sub M here, I mean the function of m-bit strings, which is the indicator for the language A on m-bit strings, is at most 2 to the minus delta m. These should all say m.
What is the AM again?
AM is an m-bit function, which is the indicator of A intersected with m-bit strings. And what is this correlation? If you recall, this is expectation over a random m-bit string of C of x times AM of x. Okay, which it's 1 if C exactly computes A of m. It's -1 if C literally computes the negation of A of m. It's 0 if C and A of m agree on exactly 50% of inputs. It's slightly bigger than 0 if C is slightly better than a half chance of computing A of m on a random input. Okay, and this supposition is all for delta greater than 0, some constant. Okay, so we're supposing if this language computable in 2 to the order n time, but if I only give you 2 to the delta m size circuits, then you can barely do better than computing on half the strings. Very strong assumption, but we'll show that it follows from a much weaker assumption. Then, well, there exists a PRG with L of n being order log n. And hence, as we saw last time, BPP equals P. Okay. So we will now attempt to prove this. We will prove it. Any questions about the statement? Yep.
Delta could be, it doesn't have to be true for all delta.
The right way to say it is suppose there exists a constant delta greater than 0 such that blah, blah, blah. And also, as I won't explicitly do it, but again, if instead you had 2 to the m to the delta here and 2 to the m to minus m to the delta here, which is a weaker assumption, then you get a pseudo-random generator where L is polylog n length, where the power on log depends on delta. And therefore, you get the PPP is in quasi-polynomial time. And even if this is just a super constant, this is super polynomial, this is sub-polynomial, then L will be n to the little of 1, and you get PPP is in sub-exponential time. But I'll just fix the parameters to the most interesting setting. Okay, so, right. So let's do the proof. Okay, so we're going to use the parameters of the design, which I'll mark with a star, where C is chosen later. And C is actually just going to depend on delta. If I'm not mistaken, I think it needs to be proportional to 1 over delta squared or something. Okay, and now we're going to define our pseudo-random generator the way I told you last time. So it's going to map L-bit strings to N-bit strings in the natural way, where G on a seed S of length n is, well, you're going to think of A sub k as a hard function. So I'll always be writing A sub k, but this is the indicator function of A on length k strings applied to sort of the capital K1 bits of S, a little k applied to the capital Kn bits of S. Okay, so there's a lot of crazy, a lot of symbols at least, but remember S is a length L string, so it's think of L as this L, and we've got n different subsets of these bit positions L, and each one has a size little k. Okay, so what we're going to do for the pseudorandom generator is for each 1 through n, extract the associated capital K sub I bits from S, let's say in left to right order, and apply this very hard function a sub k to those bits. So all the parameters are checking out in the sense that, OK, but that gives us n output bits. Let's check that it's computable in the appropriate amount of time, right? So this is computable in time. Well, it's in E, right? So 2 to the order k, which is, in our setting, 2 to the order log n, which is poly n time. OK, so that's fine. So capital G is computable in polynomial time. Oh, also, G has to figure out like what these sets are. But that's OK. It can do that in polynomial time, too. OK. And now we have to show the PRG that it satisfies this definition. And the one thing to remember, I mean, we're going to use it, is that these blocks don't overlap too much. They overlap on, at most, 10 log n out of k bits, always. Well, out of 2k bits. OK, setup OK? All right, so, well, the way you always show something as a PRG is by contraposition. So suppose this is, it's like not a PRG. Then, OK, for, this is the annoying, part infinitely many L. Again, don't worry about this too much. L. There exists distinguishing circuits C star sub n, I'll call it, well, whatever, of size at most n cubed. And bad board management, but I guess I have to write at the left side of the board here. What does it mean that they're good distinguishers? Well, it's just that if you give them either n uniformly random bits versus give them the output of the pseudorandom generator, it's good at telling the difference. The expectation in the two cases is noticeably different. So what we get is the expectation when you have a random seed of length L, and you give C star the output of the generator, versus when you give it a string R of exactly n uniformly random bits. This is noticeably different. OK, so it's just the negation of this. OK. And now, of course, we're going to apply the Yao next bit prediction theorem. That's the only thing we can do. It's all set up like that. So by Yao, what do we get? We get that there exists some I between 1 and n, and an I minus 1 bit, you say I minus 1 input predictor circuit, C prime of size, no bigger than that of C star, so at most n cubed, such that, OK, now I have to write this out. It's going to be very complicated. The expectation, when I choose a random seed of length L, and I give C prime, the first I minus 1 output to the generator, so that's A K S of K1 through A K S K I minus 1. And I asked myself, how good is C prime's output at being equal to the ith pseudorandom bit, which is A sub k of S k I? Well, this is noticeably bigger than 0. It's at least 0.2 over n. Remember, Yao had this loss of factor of n, which is really not going to bother us. OK, I'm going to draw a picture in a second, but this is what we currently have. There's a lot of notation here. OK, so this is somehow, this little I exists. This is like the key subset, k sub I. Thanks. So to ease the notation, let's say without loss of generality, let's say that this ki is just the first little k positions. So the picture here is like this. We have S. Okay, it's L bits long. And we have the first few bits. This is like S1, S2, up to S little k. And this is capital K sub I. We call this S sub first, this substring. Okay, and then we have the remaining bits, S sub k plus 1, out to SL. I'll call this S sub rest. And let me rewrite this pink boxed thing. We look at the expectation. I'm going to choose these L bits in 2 stages. First, I'm going to choose S sub rest, and then I'm going to choose S sub first. Okay, so first I'll just choose S sub rest, and then I'll choose S sub first. And then I'll rewrite everything here. It's the C prime of A applied to S in the K1 positions through A applied to S in the Ki minus 1 position times A sub K of S first. I see here that I'm using that. I just decided that Ki would be the first k bits. This expectation is at least 0.2 over n. Yes, maybe I should have made this the red box. I'll red box it again. OK, so let's imagine what happens in life when we're right here. OK, so these L minus k bits called S rest have been chosen. They're now like fixed to 1s and minus 1s. So that doesn't affect this at all. These bits here are still like they're totally free. Now that is fixed to some number of these bits. Okay, so these S of these other sets, capital K, some of those bits have been fixed when we're at this point. In fact, in a certain sense, for each of these, most of them have been fixed. Why? Because remember, these capital K sets, it's a design, so they do not intersect this capital K sub I very much. So in fact, at this point, each of these substrings has at most D free bits, like unfixed bits. On the other hand, all of these bits are still free. Okay? So at this point, like what's going on is C prime actually has very few inputs, really. I mean, each of these, in some sense, there's only D free bits here, D free bits here. And like computing A on something that has only D free bits is like not so bad. You can actually compute it in like 2 to the D time. Because I mean, it's just some function of D bits. So it's like n to the 10 time. But like the output of this is like excellent. Well, it's decent at being correlated with A, this hard function on like 100% random bits. So that's going to contradict the fact that C, no circuit C, is good at computing A. Okay, so let's make that more precise. I want to keep this around. OK, well, let's just go up here. I'm going to use the same thing I always do. So I mean, I'm just going to say since this happens in expectation over S rest, there exist fixed outcomes for S rest such that this happen. So there exist fixed S of rest setting such that this expectation over S first is bigger than 0.2 over n when S rest is fixed. Okay, so I want to keep this up. Let me pop it over here. Okay, so as I said, like once this is fixed, S of kj has at most d free bits. Unset, in other words, bits. This is for all j strictly less than I. That's the design property. Good. And this is 10 log n. Now, therefore, there exists, I don't know, 2 to the d, even 2 to the d over d, n to the 10 size circuits, say C hat sub j, computing ak of S sub k j. Good. So what I'm saying is, so now if we combine these, there's at most n of them, with C prime, you get a circuit C bar, that's a lot of decorations, of size at most. Basically, I want to say, like, I want to build a circuit that just takes in the free bits here. So, I'll use C hat 1, a function of the free bits, to like figure out this. C hat 2 as a function of the free bits to figure out the next one, up through C hat I minus 1 of the free bits to figure out this input. And then I'll plug all those answers into C prime. And so I'll get like a circuit C bar of size at most like n cubed, that's the C prime part, plus n times n to the 10. So I have like maybe n different C hats, each of size n to the 10, that I need to figure that out. Okay, so that's most, I don't know, 2n to the 11, such that the expectation over like S first, this is in plus or minus 1 to the little k, of C bar S first times AK of S first is bigger than 0.2 over n. Okay, and now I've basically contradicted this if I pick the parameters appropriately. I just basically need 2 to the delta k to be bigger than like n to the 11. Okay, so that last thing I wrote is a contradiction, provided 2 to the delta k is bigger than, I don't know, 2 times n to the 11. Is that right? Let me just double check here. So then, if I choose k in such a way that that happens, the size of C bar is indeed, it's like at most 2 then times n to the 11, which is at most 2 to the delta k. And its correlation is at least 0.2 over n, okay, which is even bigger than 1 over 2 times n to the 11. Okay, so now I'm done. So I just let k be, or try to get k to be, I don't know, like at least 11 over delta log n or something. Whatever. Okay, and I can do that because k, it's still up there, right? I still have the freedom to choose c. So like I can just make this root c. So c is, indeed order 1 over delta squared. And what is the c? It's finally, the constant in front of log n and the length of my pseudorandom generator seed. So it's fine for this to be any constant. And that's the end of the proof. Okay. Good. Any questions? Yeah.
Is there a converse? Like, if you get a pseudorandom generator, can you get some A like that?
Huh, that's a good question. If you have a pseudorandom generator, perhaps you indeed get a hard function. Where I'm just trying to think if you have given a string, you want to decide if it's in the output of the pseudorandom generator. I have to think about that for a second. But perhaps. Yeah, I mean, certainly, if that's a problem, given a string, decide if it's in the range of the pseudorandom generator. You can compute that in singly exponential time because the pseudorandom generator has the property that, you can compute it in 2 to the order seed length time. So you could enumerate all the strings and check. And then, is it hard for circuits? Somehow I'm not so sure, right? Because imagine this circuit that just, given a string of length n, just always says no, this is not in the range of the pseudorandom generator. Is it going to be correct most of the time? Because the range of the pseudorandom generator is super small. So I'm not sure it's immediate. What is interesting also, a related question that's interesting is the converse. I mean, well, we use the pseudorandom generator to conclude that BPP equals P. So you can ask if does the randomization of BPP to the P imply circuit lower bounds? And we saw a result like that. Was it on the homework? Yeah, it was on the homework. Showing that, I can't quite remember the details right now, but if you had some de-randomization, I think, of BPP to sub-exponential time, then you get a circuit lower bound, at least for permanent, either for algebraic circuits or Boolean circuits. Yeah, so there is some kind of converse to this setup. Good. Any more questions? Yep.
Are there any de-randomization results that can be proved just assuming a uniform hardness assumption?
Good question. Yeah, I was talking about this after class yesterday. So this is a bit funny in the sense that it's a bit of a mismatch between the assumption and the conclusion, in the sense that you have a non-uniform assumption to get a uniform conclusion that you have this easy to compute function, let's say an exp, that's hard to compute by, let's say, polynomial or small size circuits, and then you get a de-randomization for BPP. You might instead of ask, what if we just assume that there's a function that can be computable in exp that's not in BPP? As far as we know, exp equals BPP, but probably not. So in the next year, Polyazzo and Wigderson showed a theorem along these lines. They showed that if exp does not equal BPP, so there's the language in exp but it's not in BPP, so there's some kind of hard function for randomized algorithms, then you don't get BPP in sub-exponential time, which is what we would get if we put exp is not in P/poly here. But they get this not. It's in this class they called heuristic sub-exponential time, or some people call it pseudo sub-exponential time. And it's a very interesting concept. It's it means there is some language in sub-exponential time L. Okay, it means that for all L and BPP, there exists some like L prime in sub exp such that, well, you would like to say that L equals L prime to put BPP in sub exp, but it's only in this heuristic sub exp. What does that mean? It means that, albeit L and L prime may be different, it's hard for a polynomial time algorithm to output strings where L and L prime disagree. So I'm not being 100% precise here, but basically, no polynomial time algorithm, deterministic, can output, given n, output an x of length n such that L of x differs from L prime of x. That's not quite right. Like, this is only maybe for infinitely many, and this fails. But let's not worry about that too much. So it's kind of like, it's a very interesting concept. Like, these languages L and L prime are not the same, but in some sense, they're kind of de facto the same, because there's like no efficient algorithm that can find counterexamples to the claim that L equals L prime, except maybe for like finitely many lengths. So somehow, like, if you equate like an input x that's coming from real life, I mean, if it's generated somewhere in this universe, it was probably generated in polynomial time, whatever that means. But I mean, like some plausible looking input, it's, L and L prime are going to agree about it. I mean, there's, no way for an algorithm to notice the difference between L and L prime. So it's like an interesting concept of a way to de-randomize BPP. And if you actually look back at the proof, at the point where we decided, we're going to have a non-uniform hardness assumption about x not being computable by circuits, the reason we got to that point was like, if the algorithm you're de-randomizing, maybe I cannot explain this in 1 minute, but if the algorithm you're de-randomizing has some input x where it can notice the difference between a random string and a pseudo-randomly generated string, then you can use that to build a circuit that's good at telling apart random and pseudo-random strings, and therefore good at computing this hard function A. And that circuit you had to build really had to be a circuit because it depended on these like sort of unknown but merely existing x's for which your pseudo-random generator failed when the algorithm is run on that x. Okay, I should have tried to explain that in words, but if you look back over the proof, when we were showing like why, if you have a pseudo-random generator that BPP equals P, you'll see that like if we merely have like a hard function or a pseudo-random generator that's good against uniform algorithms, then the conclusion is merely this. We get like, a sub-exponential time algorithm that maybe doesn't exactly compute the language in BPP, but there's no algorithm that can tell the difference between the sub-exponential time language and the BPP language. OK. So good. So that's it for Nisan-Wigderson. And now we're going to come back to this. So the assumption here is about you have a language in E which is super hard to compute. It's very, very hard on average for small circuits. And that's a very strong assumption. And like, it's actually genuinely, at first, like not clear whether you should believe it. Like I kind of believe that, SAT requires full exponential time and therefore probably full exponential size circuits. But that's, in the worst case, I don't really have a feeling about like how hard is SAT on a uniformly random input. In fact, it's probably super easy because like a uniformly random input probably, has a negligible chance of being a proper encoding of a SAT formula, and therefore probably the answer is like trivially no most of the time or something like that. So luckily, later, Nisan and Wigderson showed some results about hardness amplification, which show that with just a worst case hardness assumption for E or X, but you can get these very hard assumption. So what we want in life for de-randomization is some language L and E such that the correlation of L on length n inputs with, I'm going to write things somewhat compactly here, with size 2 to the delta n circuits is at most 2 to the minus delta n. Okay, this is my short way of basically writing the assumption here. And I'm going to stop worrying about like really, we don't want for like almost all input lengths, but I'm going to stop worrying about mentioning that all the time. And you know, we have to assume something to get us started. I mean, we don't know how to prove any circuit lower bound at all, hardly. But let's make the minimal assumption of hardness in the worst case. So we'll assume that there's a language L in E such that the correlation of L with size 2 to the delta n circuits is strictly less than 1, which just literally means like no such circuits of that size can exactly compute L on all inputs. And we're going to go from here to here. Actually, let me write it more generally like this. Size S. We're going to imagine different choices of S, like 2 to the delta n, 2 to the n to the delta, or even just n to the little omega of 1. Okay, we kind of want to get from here to here. Now, in fact, the first step of going from here to here, you already did yourself on homework 8, problem number 3. Which is the result of Babai, Fortnow, Nisan-Wigderson from '93. And that was, if you recall, showing that if you have some language in exp, or it also works for E, if you go back and look at it, which is hard to compute in the worst case, then it's like slightly hard on average, where slightly hard means the correlation with the circuits is like 1 minus 1 over order n. Or maybe order n over 1 over n log n. I kind of like botched the parameters a little bit. I think it's 1 over n. But we can look back at that homework. This homework result showed that the assumption of worst case hardness implies there exists a language L prime, also in E, such that the correlation on length n inputs with size s circuits is at most 1 minus 1 over order n. Okay, to very briefly remind you how you did that, like this function of n bits, maps n 0, 1 bits to 1 bit. And you imagined like extending it to like a multilinear polynomial, and like imagine like giving that multilinear polynomial even numbers that were not just 0 and 1, but like maybe 0 through n. And like that was the L prime basically. And you use the fact that like the maybe it had to be bigger than numbers 0 through n, maybe 0 through n squared. You use the fact that first of all, this polynomial, the multilinear polynomial, which extended L prime n, is of degree n. And therefore, if you were good at computing the multilinear extension L prime on like almost all inputs, then you can compute it in the worst case on a given input by like basically picking a bunch of random points, getting the value of L prime on them, and then passing like a degree n polynomial through them to get the value of the function on the 0, 1 input that you cared about. Okay, so it's the same trick that we used to show this like passage from worst case hardness of permanent to slight hardness on average of permanent. It's 1 minus 1 over 3n thing, using the fact that permanent is a degree n polynomial. Okay, so hopefully you remember that. Yep.
It's like a minor comment. I think it was technically n log n.
Yeah, but the input length was n log n as well. So as a function of the input length, I think it's like 1 over n. But I'm not 100% confident because I looked at the original paper and they like put 1 over n squared, maybe for safety. It's not going to matter. As long as this is like 1 minus 1 over poly n, like all the things I'm going to say are the same, but perhaps it can be 1 minus 1 over order n if you're careful. So in some sense, we've gone from like the worst case assumption, like a little bit of the way there. We got from worst case hardness to like, this is usually called mild hardness. Hard to compute on like 1 minus 1 over poly n, let's say 1 minus 1 over n, fraction of inputs. And we want to get it down to like hardness of even computing on a half plus exponentially small fraction of inputs. But we took the first baby step using this trick about polynomials. I guess the fact that if you can compute basically a low degree polynomial, think of a univariate polynomial, if you can compute a low degree univariate polynomial on most inputs, then you can actually compute it on all inputs. using interpolation. OK, so now we have a function that's sort of mildly hard on average, and we want to make it super hard on average. And again, a cryptography tool due to Andy Yao is going to come to our rescue. So an even more famous one called Yao's XOR lemma. It's another example of a lemma that should really be called a theorem because it's a strong result, like the switching lemma. Actually, basically, Yao never proved it. He just kind of claimed it. And it said that he knew the proof and explained it to people, but he never wrote it down. But it was subsequently written down by many people. And it's how to turn a slightly hard function into a very hard function. And the way to do that is going to be simple. It's indicated in the title. Give it a slightly hard function f. You're going to make a hopefully much harder function g, where g takes many inputs, and g is required to output the XOR of f's values on all those inputs. Let me write it. Here's the theorem. Suppose f is an n-bit Boolean function, which is very hard to compute by size S circuits. So we're going to assume that the correlation of f with size S is less than 1 minus delta. Okay, what that means is for all circuits C of size at most S, C's correlation with f is at most 1 minus delta, which is basically means C and f agree on a random input only with probability, sorry, for at most of 1 minus delta over 2 fractional inputs do C and f agree. OK. Then we're going to construct this new function called f superscript plus k, which is going to take kn inputs. And it's going to be super hard in the sense that the correlation of f plus k with size, I'm going to write s prime here. Think of it basically as s, but it's going to be slightly different from s. Is very small. It's at most 1 minus delta over 2 to the k plus epsilon, where epsilon is a mystery right now, but it's going to go into the s prime. But let me say what f plus k is. It's what I said in words. F plus k on input like x, that's a string, x1 through xk. So this is k strings of length n, is the XOR of them, which, thanks to the glorious plus or minus 1 notation, is just the product. OK, so this is, I use plus or minus 1 notation. So this is just the XOR, the parity of f applied to all the strings in the input here. OK, and where s prime is some small constant times s times, it's actually like epsilon squared over log 1 over delta.
The smaller epsilon would take the smaller s prime.
Yes, so this is weird. But let's talk about all the parameters here. So first of all, think for a second about delta and epsilon as just being both 0.01. Okay, so the correlation with size S circuits of f is at most 0.99. And now the correlation of the XORified version is going to be small. Maybe you'll take k to be another big constant, maybe 1,000 or something, so that 0.99 to the 1,000 is also smaller than 0.01. So this whole thing will be smaller than maybe 0.01, which is 0.02, which is pretty good. And f parity k is actually not that much more complex than f because it's computing the parity of 1,000 copies of f. It is a little bit funny here in the sense that this is a small constant. This is a very small constant. So s prime is actually smaller than s, which is weird a little bit because this is a more complicated function than f. So if it's hard for size capital, if f is hard for size capital S, then f parity 1,000 times should also be hard for size capital S. It should probably even be hard for circuits of size bigger than capital S because it's a more complicated function. But the lemma is kind of weak in the sense that like it actually only shows hardness for smaller circuit size. Now, it's not like totally pathetic because it's showing stronger hardness. I mean, this is the main thing that we care about, that the hardness is like really hard. But the deficiency of the proof is that like it's only against actually smaller size circuits. That's weird. It's a kind of a function of how the proofs work. But in fact, eventually you will see that it's sort of necessary, actually. In fact, it's, as far as people know, like, I think I'm right about this. Like, this theorem could be false if you try to take S prime like comparable to S. But anyway, this will actually not bother us like too much because we'll make an assumption about like some very large S, and epsilon and delta are going to be modest enough that like multiplying S by this will not hurt us too much. But actually, delta is going to be very easy to deal with. Delta is going to be like 1 over n. So this is like log n. It's very negligible to the s's we compare it with. But in fact, like, this is basically going to be the blocking issue for like how small we can make this. Because actually, this is going to 0 like super fast. So that's going to make us happy. But you have this plus epsilon. And so how big can you make epsilon? Or how small can you make epsilon? Basically, you just have to make it as small as you can such that this does not totally cost you s times epsilon squared. So if s, maybe you can make epsilon to be something like s to the 0.01 in general. Oh, 1 over s to the 0.01 in general. Okay, so then like this is s. It'll change to maybe s to the 0.98 or something. You have to be careful. Yeah, actually, that's fine for all of these things. I mean, if you can basically take, in this case, let's say, you can take epsilon to be like 2 to the n to the 2 to the 1 over 2 to the 0.001 n to the delta. Okay, and so like multiplying s by epsilon squared doesn't really change that much. But that's basically a blocking issue here. So this is never going to be better than 1 over s to some small power, maybe. So let me even write that. So like, I'll make some more comments about this. But like, let's do some sample parameters. Actually, let me come to the sample parameters in a second. But let me say, what's the intuition for this Yau-XOR lemma? Maybe it's kind of clear. But like, here's some kind of intuition. I put it in quotes because it's actually not the greatest intuition in the world. We're going to see some better intuition later. But the most basic intuition is that, like, look, if you're trying to compute the parity x1, f of x1 through f of xk, parity is this very sensitive function, right? Like, basically, if you botch like one of the inputs, it like screws everything up. Like, having all the other k minus 1 doesn't help you if you like botch one of them. So it feels like, to compute this better than a coin flip, noticeably better than probably a half, it would seem like you need to get all k answers right. But like roughly speaking, this says that if you're a small circuit and you get a random input, like your probability of getting the answer right is like bounded by 1 minus delta, or 1 minus delta over 2. So the probability that you'll get k answers right should be kind of like this. That's decent intuition. It's a little bit off, and when we prove this next time, we'll see like a more accurate intuition, which can be turned into a proof, but that's basically the intuition. And now let me actually look at the parameters again in more detail. So of course, we want to apply Yau's XOR lemma starting from here. Okay, so what are the potential parameters? Well, okay, delta is order 1 over n. That's a gimme. So let's look at k next. What should we take k to be? Well, k better be at least 1 over n, because like if this is 1 minus 1 over n, even to get this down to a constant, k has to be like 1 over n. And then k has to be like n. But then once k is like n, like the extent to which it's bigger than n is really great. Like this will start going down exponentially fast as a function of how much bigger k is than n. So like if we want to make it go down to like something really exponentially small, like perhaps we would take k to be Actually, 1 over order n. Look at that, yeah. Perhaps we'll take k to be, for example, order n squared. That seems fine. OK, and now, so the 1 minus delta to the k thing will be like something like 2 to the minus n. So let's now maybe take epsilon to be like 2 to the minus 0.00001 times n. OK, so sort of our hardness here, this we got down to 2 to the minus n, so it's kind of negligible compared to epsilon. Our hardness is like 2 to the minus a very small constant times n. Right, so that's 1 minus delta to the over 2 to the k plus epsilon is also basically 2 to the minus 0.00001 times n. And what is s prime? Well, you know, if you know, let's take the main situation that we care about where s is like 2 to the 0.001 n. I'll say 0.1 n. This is why we wanted for like Nisan-Wigderson. I mean, our dream was to get like a super hard function where even for circuits of size 2 to the some delta n. Then we're in good shape because then s prime, which is like, you know, s times epsilon squared over log 1 over delta, basically, it's still basically s. OK, we lose a factor of 2 to the minus 0.00002 n, some other negligible factor, OK, which is like still basically 2 to the 0.01 n. OK, maybe 2 to the 0.099 n. So you might say to yourself, great, like I think we're done, we're happy, because we have this exponential hardness, 2 to the minus delta n. That's the correlation. It's against circuits of size 2 to the delta n still. So looks like we're in good shape. But there's a slight catch. Can somebody figure it out? We should also, I guess, check that f plus k is computable in E still. But it's going to be. Well, the catch is that all of these things are true, but there's one other parameter, which is the input length for f plus k. The problem is f plus k, it's not a problem, but it's like a sad thing. F plus k has input length, well, let's call it capital N, which is n times k, which in our scenario is order n cubed. So these two parameters, circuit size 2 to the delta n and hardness 2 to the minus delta n, are great as functions of little n, but they're merely decent as functions of capital N, which is the true thing we have to worry about, you know, the input length of this supposedly hard function. So what we have now is that, you know, whoa, that's me. The correlation of f parity k with size, you know, 2 to the, sorry, you know, some delta prime capital N to the 1/3 is at most 2 to the minus, you know, some delta prime capital N to the 1/3. So what we got out is something almost what we want, but not quite. We got out like this is like 2 to the input length to the 1/3, and this is 2 to the minus input length to the 1/3. And that's not quite strong enough for de-randomizing BPP to P. That was kind of like the second strongest hardness assumption that we could hope for. This is enough to get BPP in quasi-polynomial time. You know, pseudorandom generators of seed lengths polylog n, and therefore BPP in time 2 to the polylog n. So actually, given that you're only kind of going to get that out, and this is a bit unavoidable because, like, you know, k has to be at least like n to like get this 1 minus delta to the k down to something small. And then like inevitably the input length is going to be at least little n squared, and therefore like you know, the circuit size hardness that you started with, even if it was like fully exponential and little n, like it's going to be only like 2 to the n to the 1/2 hard as a function of the new input size. So on one hand, you can say, well, given that the best kind of hardness I can get out is of this form with like 2 to the input length to the constant, may as well make the weaker assumption that like, you know, that would still be fine if we had an L in X such that if this was 2 to the n to the delta, this was 2 to the minus n to the delta. Okay, so if like if our goal in life is to just get this, then Yau's XOR lemma is great for us, and the final hardness assumption we need is that there's an L, even an exp is okay by padding, such that the correlation of L with size 2 to the n to the delta is at most 2 to the minus n to the delta. Okay, and also if like we only want to get, if we only wanted to assume that there's an L in exp whose correlation with size superpolynomial circuits is at most inverse superpolynomial, then Yau's XOR lemma is fine. You know, the exponents and the polynomials change a little bit, and we get that BPP is in sub x. But if you really want the whole like Megillah and you want to get from here all the way to here, Yau's XOR lemma is not quite going to do it for you because of this input blow-up issue. But this was exactly what was finally fixed in like, well, fixed by Nisan-Wigderson in '97. Their paper, the point of it was to give a de-randomized version of Yau's XOR lemma, where you used like k-wise independence and expander random walks and other like known concrete pseudo-randomness techniques, basically to like get an equally hard function that maybe uses something more like order, that has capital N more like order n plus k rather than order n times k. So you have to like look into the proof technique of Yau's XOR lemma, which we're going to do in the next class, and you know, cleverly figured it out so that like these are not fully independent n-bit strings, but they're like merely sufficiently independent strings that the whole proof still works. So we're not going to do that. So we'll just prove Yau's XOR lemma next time, because it's a very enjoyable proof. And so I guess that will have at least given us this, which is, you know, good enough. OK, any questions? OK, so the final plan is on next Tuesday we'll prove Yau's XOR lemma, and then the last class we'll do something, probably circuit lower bounds for ACC.